morning all. Good morning all. We've got a nice chat today. Let's get interdisciplinary Rust design patterns for chemical plants. Thank you. Give them a warm welcome.
Yeah, thank you very much, and welcome stations in London, and welcome to those on the video streams. My name is Tim Janos, and today we talk about design patterns in Rust. And I believe we find a lot of great ideas in design patterns, and they can empower us software engineers with better communication. And also this talk is towards software engineers. I dream of a world where safe and fast software written in Rust empowers the engineers in other fields to build the chemical plants of tomorrow. So besides that, there is this motivation I have to share this nice application example with you. I think history is important, so you get some cross-references here. And I hope I sparked some thoughts, and if I did, come to me, talk to me. I'm here for talking to you guys. And last but not least, interdisciplinary collaboration becomes more and more important. And think about it, we as a Rust community, we are quite cross-disciplinary already, right? We have those guys from the embedded programming and guys from the web development. And that's often comes with different backgrounds and terminologies. However, today we will start with an introduction to what are design patterns, what are chemical plants, more in the sense of how do we represent them in a computer. And then we will talk about two very common patterns in Rust, the builder pattern and the type state pattern. And they empower us with safe and ergonomic APIs. And after that, I want to share my mixed feelings with the visitor pattern with you, but help to decompose some ideas from it. All right, what are design patterns? I searched the web and I found a nice definition on Refactoring Guru. So it is, design patterns are typical solution to common problems in software design. Each pattern is like a blueprint that you can customize to solve a particular design problem in your code. And I think customize is quite important here. They consist of like a name, short name, 2 words, 3, a problem description, a solution proposal. Normally you also find relationships to other patterns and some examples, but on this slide I want to focus on the name, a short problem description, and the solution. So you will see this slide again. And yeah, here's the first cross-reference. This idea around patterns started in 1994 with the book Design Patterns, Element of Usable, Object-Oriented Software. It was published by the Gang of Four, and this was a context when C++ and classes, like early object-oriented programming was around, and also the Java world got on pace. And they had like a peak popularity around 2010, I think. And I saw some opinions in the world of in our nice internet here. Enrique, for example, says, people who think design patterns aren't that important have never maintained a software for more than 1 year. So it's a bold statement that supports this talk quite good. However, if you dig a bit deeper, there were a lot of people expressing concerns about patterns. And that is due to the fact that we have this tendency as humans to see, like, when we have a hammer, every problem becomes like a nail, right? And yeah, so remain open-minded. And for me, it's really nice to put like short words to maybe complex topics, and to remember myself when we do this to always question the common understanding. And there's a zoo of pattern around. We will just focus here on 3. I think there are probably 300 around. And sometimes it's a bit hard to see like the boundary. Some design patterns are quite small, others go in the direction of already being like a proposal for architecture of software. with this short introduction, now get ready for what is a chemical plant. So, as you might imagine in a computer, we represent it as a cyclic graph structure. And the nodes you have that are like, they are called unit operations in this flow sheet, like a reactor, a distillation column, a compressor, and you have edges that represent pipes where these mixtures of gases and liquids were brought through the plant. And here's a schematic example. It's a lot. It's of a very popular process. It's called the Haber-Bosch process for ammonia production. This is for fertilizer and keeps us all well nutritioned because it's very important for the food delivery. Yeah. However, what I want you to take home from this is that nearly every chemical plant comes with 3 parts. First, we have this upstream where we want to get our ingredients ready, get the right temperature of the mixture, get the right pressure. Then you have a main part. This is sometimes one reactor, like in this flow sheet here with the Haber-Bosch, and sometimes it's a cascade of reactors. And after this main reaction, you have the so-called downstream where you try to separate products from wastes and recycle back reactants. So this was very schematic. However, I reached out to BASF, who provided these nice pictures. You cannot get them so easily because you're not allowed when you go for exhibitions there to take pictures. And here, as you can see, like the plants are really big. We have like 2 humans there with yellow helmets. And yeah, that is actually an ammonia plant. And in the end of the last century, BASF was at the forefront to solve the hunger crisis, what was like the climate crisis of the last century. And now a lot of people are working on this new crisis. Okay. We will focus in this talk on one specific unit operation for our patterns, a distillation column. And all of us know it when you maybe saw like an evaporation of wine, and then the gas has a higher purity of alcohol, and that is how you could like produce brandy. Like you heat it up, the liquid evaporated, and that is how booze is made, or was made at least for a long time. And in this distillation columns, you normally separate mixtures that have different boiling points. So the low boiling point components were extracted on the top, and the other ones on the bottom. And in the computer, we will have variables to describe this distillation column. For example, the number of stages is representing the height, and also like where are inlet positions where we put our feet in, like this distillation columns. Then there are other variables, like you can control temperature and pressure to some amount. And so now we know what is a distillation column. Let's build one, right? And that's a nice transition to the first pattern, the builder pattern, that is responsible to, when you have like a complex object, and there are a lot of coupling fields, and you want to initialize that. So that is like the problem the builder pattern solves by proposing the solution that we add a new object for this that is responsible for the construction. So we have a separation of concern here. And for our running example, we will now construct a column in a way that all these requirements we have, like you need at least 3 stages because you have a reboiler, at least 1 distillation stage and a condenser in these descriptions, and there are other requirements. And the builder pattern is very often seen in Rust, because in contrast to other languages, we don't have function overloading. And so that's a nice way to go around this obstacle. So we will now start by just introducing types in Rust. And here you can see a struct with some variables that we saw before on the previous slide. What I highlighted here are derived macros, so the common one, the debug trait, default, and so on. They add functionality to our plant. In our case, the default trait is used in our distillation column builder that just popped up. And this is a struct that just contains the distillation column, and we'll build it now in this example code. And well, in our new function, we use default, and then we have like 0 stages, no feed positions, so everything is invalid. And as the next step, we need to have ways to change this. And you find it in like 2 common variants. There's one variant where you take a mutable reference. This is this ~mute self into the function, and you return this mutable reference. This allows you to use the dot to call another function afterwards. This is also quite good when your builder is big, because when you would move or copy around something, that may be not so beneficial. However, there's this other variant where the & is missing. That means we consume the variable. That means self moves into the scope of the function, and then this function is the owner, and afterwards we return self. So it's a different thing. And this variant brings one big advantage. You could return something else than self, and that is what we will see later about type conversions. And yeah, besides that, I decided for this talk to do a very, let's say, UI near error handling. So I wrote this method here, check error, which returns a result. It's highlighted again. Yeah, I think most of you know result. We have a OK type, which is empty, and a string for the error. And internally, that's not what you would do in like idiomatic Rust, but I decided here to just fill a vector with all the errors, and then you could put it out when you build a distillation column that is invalid. And at the end, we just check, is the vector empty? Then everything is OK. We return OK. And otherwise, we will join the strings with new lines and return the error. Maybe a small addition, when you want to do error checking in like a library that you provide to the outside, you should check out the create this error. And anyhow, for when you're writing a program, and well, the build method then also comes in 2 variants. You can either consume self again, and this helps to save a copy, because we can now move out this data structure of the distillation column. And the other variant would be you want to build and reuse it. This is beneficial if you want to use a builder to build many of those objects, for example. Yeah, let's see some example usage. You often find this in some Rust code. Here in the example code, we just generate a builder and use this method chaining to set up the variables, like stages 32 and so on. And then we use build and reuse first to set up this distillation column. and match if it's okay or an error. And yeah, debug print out the result in this case because we are okay here. So we just see the variables. Then the following code, we clear the feed position, set the stages to 2 just to demonstrate, okay, there are some errors now collected during the build method. And this is like really a idea you would more do in like older language like C++ with collecting these error messages. We will see nicer ways with generics in the next part. And what you can also do, you can reduce a bit the builder plate when you don't want to start writing your own stuff. But for example, with a type builder crate, you can use macros on the, let's say, main struct to define your builder and the behavior. All right, so that was like the first very simple pattern. But now we will build up on this with the type state pattern. And we want to add some states to our distillation columns. And normally you face this problem that you have data, and depending on the state of this data, you may want to have different behaviors, and for the type state pattern, particular different interfaces depending on the states. And the solution here is like, now we want to extract those interfaces in separate structs or types. And we already saw a first very simple example with a 2-state pattern where we have the builder as one state in construction, and as soon as we call build, we move into this other state. Like the builder is gone, and we really have like a new type here, distillation column, and it's ready for use, let's say. But it gets more interesting, you see, when there's like a more complex column, like a divided wall column. There's just a wall inside, but it helps you to separate more than two, let's say, mixtures out of this distillation. And then you could add like another builder for the divided wall column with more complex methods, and this would also have its own build method going into another state, producing a divided wall column. There are also examples, let's say, in the standard library that are quite close to type state. That is all related to how did we came to the generalization that we nowadays have with the type state pattern. And instead, we have this file open method that generates our file, and we are safe that it's opened then when it works. That's not true in C, for example. You just have a file handle and you never know if anybody did close it or not. So we have some luxury here, some safe and ergonomic. And when it's dropped, we are out of scope. So that's happening when a variable goes out of scope. In C++, it would be the destructor, and then Rust handles the file closing for you. And this kind of idiom was called resource initialization. Resource acquisition is initialization in C++, and it's also like some kind of a two-state type pattern. And there are two common implementations. We saw like with external types, we just used several structs that were moved into each other, transformed. We have the self-ergonomic API already, but we have problems with providing common code for like several states. And for this reason, what's done nowadays in Rust is we use the traits and generics to define our type states. And this allows us to have like common interfaces over all states, for example, with an implementation block. And we will now see this in the upcoming example. So we still want to model our distillation column, and here we will use 3 states. First, after the building it's configured. Then, like I come from a background where modeling, simulation, and optimization is interesting. So you would get the data structure ready for simulation. That means generate the equation system. And you would simulate it then, and then you have a simulated distillation column which contains some results. And besides that, from each of these stages, you could have a method changing the parameters, which just moves back our distillation column in the last state, in the initial state, sorry. And yeah, here, just the types were added. So at the bottom of the boxes, you can see type state column as the name of our new struct, and then 3 different generic type parameters configured, ready for simulation, and simulated. And well, yeah, that's a lot now, but we want to encode the states for Rust, and for this we work with empty structs, which are 0-size types, to tell the Rust compiler about what is happening. So for each state 1. And we have a trait called column state, which is implemented for each of those structs. And this really helps to ensure that we never can go into another state when we're using column state. So that's the encoding of the states. And what you then do, in our case, we just wrap the data. We take the distillation column as data field. And when working here with the generic type parameter S, which needs to be a column state, we don't instantiate it, but to help the compiler to reason about it, it's in this phantom data marker type. So that's just a 0-size typed. And that is like the core struct for our now type state pattern. And then you can start to add transitions with different implementation blocks. So here really where the magic happens is in the upper line, impl type state column, and then you choose the ready for simulation state, and in this implementation block you implement simulate. And I also marked the signature of simulate here because it consumes self and returns another type, which is just different in the generic parameter, in this state parameter. And yeah, here we generate some the return value. So it's just moving our data to another instance. And if we want to add common functionality, we can just use bounds on the traits. Here in the above line, we have impl s for all column states, and then we add the change parameters method here. And you can see the method in detail in a GitHub repository. I will share this later. Yeah, so that is the idea how you can work with it. However, this is also the good spot to thank like 2 persons. First of all, Chiara, who is organizing the Rust and C++ Dragon meetup. She gave good feedback to this slides. And the next section is, it was added now after my former colleague Jens gave me some feedback, and he has a background in chemical engineering. And why is it so cool? He didn't understood why this is cool for a programmer. He was like, yeah, you're sticking to the rules, but why is this cool for a programmer? And it's cool for a programmer because in your IDE, you just get the interface you currently have in the state. And this is just 2 methods in configured here. Change parameters, generate equations. And as soon as we go into the other state, one method goes away and another transition method is added. And yeah, we will also talk about iter equations later, because the other state transition, which is then just add method like get me the temperature profile of the column, get me the pressure profile, and so on. Like now we can access the results because the simulation is done. And what we didn't see so far was how do we do like iter equations now for two structs. What I did in the example code is I just introduced another trait, and this trait could be quite complex. Like think about the iterator trait, or look at it if you didn't do it yet. There's like one method you have to implement, and you come with so much functionality, and you can do it the same way for like subsets of states here. And this state column with equations, a trait, has to be then implemented for each state that needs to support it. I'm not 100% sure, but probably you can also reduce the boilerplate here a bit. So if one of the more experienced guys know, let me know. And yeah, with that said, now look at some example code. And in this example code, we start with a column that was in the end generated with our builder. So there's a helper function, build distillation column. And then we just debug dump the content of the struct, and we use the generate equation system method and put out the equations. So that is the output on the right-hand side for the code. And yeah, then we can just continue to use this, and in the IDE, you would really only see the methods you have at the struct. Like all these let columns, they are shadowing each other, and they're changing the types of a variable. So it's always called column, but internally you have another state, and by this another interface. And as soon as we call this change parameters, we go back to the former state. And when you look at the output at the button, you can see the marker which has like this type argument with configured in it. Yeah. You can find this example code on GitHub. Here is a link for it. And yeah, before I move on, I will drink shortly. Very well, because we will revisit the type state pattern. There is, let's say, I just wrote up some example code to show you how you can start playing around with it. But there are there's a possibility to have a really type state builder, for example, and this is important if you want to have a bulletproof library. And you do some investment then at the library level. You have the safe and ergonomic for the library users. And for example, in the Ragnar client of Lucas Putz, it's used there. And here you can see a lot of generic parameters. And the interesting thing is on the lower code, it's not highlighted on this slide. Let's see. Like you have here's a unset, and here's a set. So it remembers which variables are already set, so you can only set them once, for example, in this code. However, it would be a lot of boilerplate if you store all the variables in the builder. However, there is a nightly feature used in this repository for it. So it will be someday stable, I guess. Okay. Yeah, now we get to a more controversial part, and you can imagine that because you you're a programmer sitting in your basement, and I was literally programming in a basement because my parents had the computer in the basement. And when you have a pizza and Coca-Cola, and then the doorbell goes, and you were like coding a game. Visitors? Mixed feelings. And yeah, we start with a slide here. The problem is already like a well-defined object structure shall support and might be extended with several algorithms. Like I tried to like condense it in one sentence, and the solution is add a second hierarchy that visits the objects to implement the algorithm for each object type. And when I put myself in your shoes now, like just imagine hearing some of you first time a visitor pattern, it will be like, what? Before that, these template slides would be probably much more understandable. And I also found some information about visitor on the internet. My own service said like, yeah, that's not so nice. It's the most controversial. And also Traf came around with some studies about patterns, and most of the replies said, like, they asked people, and most of the replies to the patterns was, yeah, they're good ideas. But for the visitor pattern, it was like mixed to say. And yeah, Jonas Kuckenberg, he will have a talk on RustNL about an operating system, and he was also thinking about applying the visitor pattern and said like, no, normally you don't need it. And you don't need it all, but there are good ideas in it. And yeah, to close the circle, we will now bring this example from a chemical plant flow sheet and how you could extend it. Like you have this well-defined set of objects which are distillation columns, reactors, and so on. So here you're really thinking about like types, like a class hierarchy. Like you have a unit operation and several subtypes that are different but have a generalization. And on the right-hand side, you have an extension point, and in chemical engineering, that may be provided by the manufacturer of a pump who has a model for this pump, how it behaves. And they give you a binary, a DLL, and yeah, that's what you have to work with. So you can then implement different algorithms on these objects with a visitor pattern. So that is what the visitor pattern is in the end proposing, like separation of data structure and functionality in a very complex setting. And I'm sorry, we need to get a bit more detailed here to really understand why visitor is so misunderstood. And there are this concept, static and dynamic dispatch. Many or some have heard, and double dispatch like is rarely known, I think. And both dispatch type, they resolve a function by a receiver type, like by the type of self or the this pointer in C++. And static dispatch, on the other hand, it is using really generics and defined types. At compile time, it's very efficient, and that's how you do it in Rust with generics and bounds. No new types at runtime, so the manufacturer cannot plug in some functionality. Therefore, you need dynamic dispatch, which occurs at runtime, but therefore you normally have like a table of function pointers and an indirection stored in the data structures. And in Rust, you would use a trait object, which is like putting your traits into a box with a shared pointer onto the heap and using the dyn keyword. And then you get some flexibility with unknown types. And double dispatch, well, that's what the visitor pattern is doing, and I think it's easier to explain at a diagram. And that is what actually is shown in most of the early literature, this kind of diagram. So on the left-hand side, you have a unit operation, which is visitable, and there's a function called accept. And there you take like really a dynamic object that is we solved at runtime of a flowsheet extension, and on the right-hand side you would use a visit method with also dynamic resolvable types. That is the original proposal. You find a lot of first thing first. That was what I did in a C++ project for optimizing chemical plants with an external simulator. And I have this mixed feeling because like you're working on this hierarchy, a type hierarchy, unit operations, but you often or nearly always have a container too with a hierarchy like trees and graphs. And so you also get traversal into this mix. So it's good to have the separation of concerns there. And yeah, sometimes, and that was what was missing in my implementation first. And to be honest, equation systems are quite similar for every unit operation. It only makes it different if like discrete decisions like the number of stages changes your equations. So in my case, the distillation column was special. Everything else could be handled in the same case. So it was a bit of an overshoot. Nonetheless, it works. What is bad is like when you stick to the pattern, you should really end up with the object hierarchy to be well defined, because when you change it later on, that is a change you don't want to do because all the visitors have to be changed then. And yeah, what I thought was coming first here on the right-hand side, normally you don't have double dispatch everywhere when you find the visitor nowadays. So often you just use types there. It is in the original proposal though, and yeah, that leads to some misunderstanding. Well, we got a bit sidetracked here. Nice history lesson. However, let's get back on track. And where is it used in the Rust ecosystem? Well, I first find it on Google in the Rust design patterns book, and they were also proposing like having the traversal separated from the object hierarchy in method prefixed with walk. And then Zerde is one example that comes to mind when visitors are used. And Zerde uses this derived macros we saw earlier. Here on the right-hand side, I just added deserialize and serialize as derived macros, and that means, okay, my struct can be stored in some file format, right? And internally, this deserializer that just gets generated in procedural macros is then forwarded to a visitor. And the visitor himself is then implemented for each file format, like JSON, RON, protobufs, or whatever you want to use. Yeah, I didn't find so much about double dispatch. It's not so common in Rust anymore. But what I found was, at least in the mid-level intermediate language package, there is a trait visitable and a trait visitor, and this could, like you as implementer could decide if you put like trait objects into something. I'm not 100% sure how the compiler guys do it, but like this is at least the same. Double dispatch ideas could be supported there. Okay. Besides that, they have also nice, let's say, rules of best practices with a super method and a visit method. The super method is just a default implementation. Yeah, and here in a compiler, you normally work on a tree structure, which is like an abstract syntax tree. Yeah, but to summarize, in the end, we have so many topics here, algorithms and domain knowledge. It most often, because you need to have this well-defined object structure, you need to get the domain knowledge in. You have this distinguishing between object hierarchy and the container, which might be a tree or a graph. And we heard about these details. So there is so much you see inside the visitor pattern, and that is why I think there's a lot to learn. And you can also learn from things that are complex and by decomposing them for yourself, for your own use case. So finally, we did it. We learned a bit about the Haber-Bosch process, how you could represent this in a flow sheet. And we then focused on distillation columns, which are in fact the most common separation operation in the chemical industry. And we learned about the builder and the type state pattern that are very well used in the Rust ecosystem. And we decomposed a bit of the complexities of the visitor pattern. And I promised you some cross-references. So I think in November I started a video series with a mate of mine, Jonathan Ayala. It's called Pragmatic Rust for Engineers. And then 2.5 hours of videos, you will simulate a reaction, you will visualize it, and you will, in the third video, have like this closed loop with a user interface in WebAssembly. Like you can change some sliders of variables, change the number of reactors, and you see interactively how this is changing. And if you're interested in history and how Haber-Bosch solved the hunger crisis, check out the blog post of Jonathan. So thank you very much, and I'm happy to, looking forward to discussion.
Tim, we have about 10 minutes.
Hello. Thank you for the talk. It's very interesting. I'd like to ask about the type state. Actually, in Rust, they also provide, enum, where you can provide that, solve that very neatly for the representing the state and the type. And you also can do the transition as well from one to another. So why don't you use the enum for the type state pattern?
You could use, I think enums are sometimes used to store like like a container with different states. Let me think about it. In the end, you would end up, when you have an enum in a variable, you always need the match arm, right? So you want to go one level lower. Yeah. So. But the enums, that's good that you bring this up. It's really useful if you want to store it in containers, because you can end up with like some difficulties with like the variables I showed here when you want to put it in a container. Okay.
Great talk, thank you. Quick question about your feedback and your what is your sense of the difference in the experience between implementing this in C++ a few years ago and then going to the Rust implementation. And the following question is just then, is it used kind of in just for simulation in R&D or actually in production systems?
So my C++ framework was in a research project, and there, let's say I had like his own multi-threading solution there, and there were a lot of bugs, so I was really welcoming learning about Rust. So I had deadlocks sometimes in the optimization, and how you work it out when you don't find the deadlock first. I found it in the end someday, but I just was accepting that some optimization break, it's too early and won't continue. Like Rust brings so much more yeah, help to me. Like, I'm just a human being, and I like to work with complex systems, and Rust helps me to not shoot in my own foot, and C++ does this. Yeah, on the other hand, I really love to, like, in this video series, I also ended up to provide a contribution to the ODE solvers crate, and like, the experience just with the ecosystem is so nice. You can find so many yeah, good tools and crates online. It's much harder to, like, integrate this in a C++ project, because there the tooling is so bad for getting external libraries in. So, did this answer your question, or?
Any more questions? Okay.
We now break for half an hour refreshments. Thanks again, Tim. Give him one last round of applause. Good morning, all. Today we have a talk from Konstantin on Java and Rust integration. Give him a warm welcome. Thank you.
Well, good morning, everyone, and thank you for showing the interest to my talk today. Just a quick introduction. I'm Konstantin. I'm a software engineer at WhatsApp, based here in London. Through various initiatives, well, I had some privilege to ship some common shared Rust code base across a family of mobile applications and some desktop applications. So I'm here today to share some insight and knowledge we've gained, just things which seems to work for us, and with particular emphasis on the JNI bridges, Java native interface bridges. So this is going to be quite a low-level talk on how JNI works under the hood, basically. I will though start with some basics, so the colleagues who might not have some context still would be able to follow what is going on. So since you're here today all, I assume you finding yourself in this situation where you have parts of your application written in Java and some other parts written in Rust. And presumably you're looking for the way, how do we make them to integrate? How do you make them to talk to one each other? And before diving any further, I would actually pause right here and ask you to consider whether this is actually optimal route and indeed the route which you want to follow for your project. Because bringing a foreign function interface on board would introduce some complexities in both development and maintenance. So you should know what you're signing up for. Historically, there is a large number of technologies which facilitate inter-process communications, right? There are alternatives. Maybe you can make your Java part as a microservice and make your mobile application, for example, written Rust part as a microservice and mobile application written in Java, talk to them over like REST or like gRPC. Maybe you're actually building some sort of extract transformation loading pipeline, and you can just make parts to talk over like files or databases maybe. So having them separate as separate executables give you a lot of advantages. You have dedicated teams. You only have experts in one language working on one project. It is simplifying debugging. You don't have the case when you have to like figure out how do I debug Rust in Android Studio, right? You don't have this because you just debug in Java and debug in Rust separately. You have standard interface. You can even replace Java tomorrow with Python, for example. I assume no one wants to replace Rust here. And you can test it's in isolation. Obviously, you have the well-defined API bridge. You don't have any unsafety which you bring when you're doing FFI naturally. Well, okay, maybe you're confident that you need it to be within one process. You want Java and Rust share the same process. Consider if you have right architecture. Maybe you don't have to write JNI bridge. You can take some high-level solutions. For example, I think During the next time slot, the colleagues from Red Badger will do a hands-on tutorial on cracks, which allows you to build like applications with Rust, and you might not need to write any bridge yourself. Well, okay, all right, you decided you want Java, you want Rust in the same process, you want JNI bridge. So there are essentially two approaches, two ways, principally, how Java can talk to Rust. In the most common scenario, you have like a Java application, Java main method, which starts, then it somehow loads the native code. Usually you will pack your Rust code as a dynamic library. And there is a thing called JNI calling convention. It's basically a specification which says how you need to name the functions in particular way, declare them in particular way in the binary, so Java virtual machine can find them and execute your native code. Now, your native code wants to interact with Java virtual machine somehow, and there is a JNI APIs provided for you to do so. The JNI APIs are essentially just like a header file. It's called jni.h, but of course we have a Rust bindings for them to make it easier. It would be unfair not to mention the second approach, which I've seen in industry. It's far, far less common, but it exists. So technically, you can have Rust main method. It just starts your Rust application. The Rust then can load Java virtual machine as a shared object, call JNI APIs to start Java inside Rust, and then run some Java code, and the Java code can actually call Rust back using JNI calling convention. You can even have two virtual machines, or 3 or 4, running in the same Java process. This could kind of happen in some legacy software, which was like written early in C, and then they decide to have, we want to have fancy Java plugins or something like that. That's where I've seen it, maybe in some embedded software. So most often you will be on the left side always, but what is important is that JNI calling convention and JNI APIs, they're always the same. Now, when we consider integration of Java and Rust, the foremost decision lies in like how we will transfer the complex data beyond just primitive types, integer and strings, between two languages. And from my perspective, there are like 3 principal approaches. The first option, which naturally comes to mind when you start, is just to utilize the JNI APIs, which we talked about briefly recently, to manipulate Java objects directly. So when JVM calls your code, it will pass you a class. You can then iterate over the fields, get the values out of the fields, convert it into Rust, and then do something. And likewise, when you need to return value, you create an instance of Java class, you fill the fields in, and you send it back to JVM, right? That's going to work. It's essential here to ensure that like the structure of your models is aligned. So if you make change in Rust, you need to make the same change in Java. There's a key caution to keep in mind. If you use minifiers or code obfuscators, they will rename, they might even remove some fields because they believe they are unused, and then it will cause obvious problems. So ensure to put the proper annotations for them. Well, while this road is very flexible, you can write any JNI bridge, you can make it to look like you want, it also involves considerable effort, and you find yourself writing and maintaining a lot of like this boilerplate glue code, which grows over time. So second option, alternatives, which normally people start thinking like, oh, well, I don't want to write them, I can just generate them. So it looks appealing, but the trouble is the number of open source options are actually like limited. I know about like Unify, but it just mainly does Kotlin. A lot of people end up writing their own generator either based on some schema, domain-specific language, or writing a procedural macro. Then you have like Rust as a source of truth. It might work for some projects, especially if your APIs are following some patterns that are very similar, for example. And the simplest option, actually, and the option which surprisingly very often overlooked, is to just use serialization. So there are a lot of serialization, most of them were developed for inter-process communication. Some are faster, some are slower. You can take, for example, well-known protobuf, not the fastest, but you have a schema. Everyone knows, it's at least well-tested, well-maintained. You have a well-used code gens for both Java and Rust, so you just define your schema in a schema file, generate the bindings, protobuf bindings, and then your JNI interface is as simple as a function which accepts byte array and it returns a byte array, and that's your JNI bridge. So it's a huge advantage. You can then modify your models whatever you want, add new messages, well, in part above they call messages, and you don't actually need to change your bridge code, which is unsafe, low level, and maybe you don't have many experts in your team dealing with that. So you can decide what works for you. In this presentation, I will use protobuf. It's not the fastest, but I think I was just hoping most of people would be familiar with it. So I defined a request message, which contains a string and some delay to emulate the delay in response. And I have the success and error cases for responses. I can then just take an open source, well-maintained libraries, generate the code to convert, generate the Java classes and Rust structs to represent that schema, and it will give me methods to convert them from and to byte array. So that's very simple. I also show examples of how to do the first approach in the code later on, so you will also get knowledge about that. So now, okay, our schema is defined, so let's look back on Java native interface calling convention. And if you ever wondered how actually Java talks to native code, this is where the magic happens so far. We'll look on the C example first. So on top, you have a reference to Oracle Java native interface specification, and it provides, it's our source of truth for the APIs. It's described in terms of the C APIs, which we're not going to use directly. We'll use the Rust wrapper today, but it's quite easy to reason, by looking on the wrapper, maybe sometimes looking in a little bit deep in the source code of a wrapper to see which API call is going to be called under the hood, and so you can figure out what's happening. So that's how JNI works in C and in Java. In Java, you declare a method with a native keyword, and there's no body in this method. You can pass parameters if you want. You can make it static if you want. It's all supported. So Java calling conventions then requires you to declare a method in your binary, which following the JNI call convention. The name is part of the specification. It should start with Java, followed by the package names and the class name and the function name. The arguments are also specified. The first argument is always a JNI interface pointer, which provides us access to Java native interface APIs. Then if your method is non-static, then the second argument is this pointer, which allows you to access class all the data about the instance, for example, fields. And then you have your arguments. So it's important to know that Java must load this binary before calling any method on it. And the binary is usually packed as dynamic library, so shared object, for example, in Unix systems. Now, when you compile a shared object in Rust, each shared object will have its own copy of Rust standard library. And if you have 4 Java projects, which you want to ship to your 4 Rust projects, which you want to ship to your Java application, then you will ship 4 copies of standard library. And for mobile apps, it's kind of a problem, for example. So it might work to compile, have a top-level crate, compile all your crates into one dynamic library, and then ship it and load it once, so then you have only 1 copy of standard library. Just a trick to save a binary size. Okay, so let's see how our JNI bridge will look in Rust. So you can see here on top a Java method, which which just accepts the byte array and returns the byte array, which are going to be our serialized protobufs. And this is how it's going to look in Rust. So I'm using the third-party crate called JNI, which provides a nice little secure wrappers for otherwise unsafe C APIs. So the name of the method should be the same, following the same calling convention as we talked. You should tell compiler not to mangle with the name, and we annotate it with external system calling convention. Then the first parameter again is interface pointer, this pointer to this, and the Java byte array is passed this way. So the method body is quite simple. We have written 2 utility methods, which we will look shortly, to actually convert this Java array of bytes into the Rust string and then convert it back. We'll convert the response back to Java byte array. And then our business logic is just simple if statement to simulate success and error conditions. So let's dive in to convert in Java byte array into the Rust struct. So the key thing, obviously, is just to access the bytes. Once we have it, then we have this self-decode method, which is provided by the protobuf library to construct the deserialized Java struct from the array of bytes. So technically, our question is, how do we get like Rust slice from the Java array of byte ideally without copying? So that slice is the Java byte array. It's actually allocated on Java heap. So there are 3 different APIs to do to get like a pointer to it, to get access. One of those, or kind of 2 of those, actually involve copies. So the fastest is this pair of get and release primitive array critical. Now, we don't call them directly. Java, or Rust JNI crate provides us a nice wrapper, which returns a word. So we can dereference it to actually a slice, unfortunately signed, because bytes are signed in Java, or we can cast it to, to one side, and then convert it unsafely to Rust slice. And once we drop the word, the release primitive array critical API would be called. Now, converting it back is even more straightforward. So we have a Rust struct. We can use a library serializer method to serialize it back to array of bytes, or vector of bytes. Unfortunately, all bytes arrays which we pass to Java have to be allocated on the JVM. So we have to copy bytes here over the bridge. And we have a wrapper across the JNI APIs to actually construct a Java byte array from the slice, nice and simple. Okay, so far, now we know how to make Java to call Rust. Well, let's try something a little bit sophisticated. And how about we have this JNI callback, which also accepts bytes arrays for now, and let's make Rust to call it back to Java from some background thread. So if you look to Oracle Java documentation on JNI bridge and on our wrapper, JNI crate, we can actually figure out that this is quite simple to do. There is a call method routine, which we can call, pass the object on which we want to call, and the name of the function, the signature, and the arguments, and we'll just call that Java function. Now, what's important to note is like we need this env, which is JNI interface pointer, and we need this J object, right, to be called. And we want it to be called from the background thread. So if we try to do something like below, in like that 4 lines of code, it will not compile. And this is why I love Rust so much. It's also like my favorite example to show to people when they come to me and say, hey, your Rust is actually not safe, it's all fiction. In the end, you call, like, you make unsafe calls and everything's gonna crash. So you would never imagine when you write a FFI bridge and there's some kind of like help which compiler can give you, you would like expect, well, actually all bets should be off, right? I'm just like, it has no way to know like what shall I do with this Java, all this like interface pointers and stuff. But in reality, because this JNI crate, which we're using, has designed well, has nice abstractions, they actually allow us not to shoot our own leg. So if you do it in C, this code in C would just compile. You need to go then and read the invocation API chapter of this documentation, and you will learn 2 things. First, you will learn this JNI interface pointer is actually thread specific. You cannot move it across thread. You cannot call it across threads because it relies on some thread local variables under the hood. And the second thing is this J object is managed object, it's garbage collected object. So you see we spawn a thread here and the native call method immediately exits, right? And technically Java is allowed to just garbage collect this J object if it doesn't have any reference after that, because maybe no one is referring it. So we actually need to tell Java that, hey, please preserve this garbage, object and don't garbage collect it. So because JNI env and JObject have lifetimes, and because they don't implement send, the compiler doesn't let you to move them to another thread and allows you to avoid this mistake, right? So the Java virtual machine provides you the APIs to actually get the first to get like it's called global reference, which is basically increasing reference counter for this object to prevent garbage collector, and that global ref is now send and static, so you can move it across thread. And when you have a valid interface pointer, like here, before you spawn a thread, you have it. You can get the pointer to virtual machine, which is associated to it, which you can also move across thread and then attach a new threads, background threads to it. So that new global reference is actually like a pattern, which I have seen in almost every managed language to where I've written the bindings to. So I've written bindings to C#, I've written it to Swift as well, and the same pattern prevails there. They just have slightly different terminology. I think in C# or in Swift they call unmanaged instead of global. So the idea is the same. You have garbage collected object. You want to preserve it in native code for some time to use later. So you must ensure it's not collected, and so you kind of need to call some API usually to avoid that. And the nice thing that Rust, even this is not even about Rust, it's about other language Rust talking to, it can enforce you to do that with the lifetimes. So, well, to make it simpler, we will just write like a helper struct, which is called callback context. We store these two objects in it, in a new method. We obtain them using the APIs I shown. Now, this could be moved across threads because it's a send and static. So, well, so now we can actually modify our code, native call, and we can create the callback context. We can move it to the thread, like sleep for a few seconds, and then call back to Java. We'll see how to do it in implementation of this callback method. So it's important to remember that you cannot just start making calls to Java in an arbitrary thread. The thread should be specifically registered, or it's called actually attached to JVM before making any call. And attaching is, you can think about it, you just set some thread local variables, including like exception flags, for example. It's not a free operation, so you ideally want to minimize number of times you do it, but you can do it anytime you want, technically. So this is how it looks in Rust. So attach current thread API is nicely wrapped into a GWT as well by the JNI crate. The GWT could be dereferenced to the JNI interface pointer, which is valid for this current thread. And you can just call, then you can just do the call method, which we briefly discussed earlier now. Now, when you drop the GWT, you will also detach current thread, so you can preserve it for as long as you want the thread to be attached. Because you need the interface pointer to call the call method on it, and because the interface pointer is not send and not static, Java actually enforces you to follow this API. Rust is actually enforcing you to follow this API pattern. Cool, we learned now how to call from Java to Rust, and we learn how to call from Rust back to Java. Yes, but let's make things a little bit more fun, and let's see if our Rust code is asynchronous now. Okay, so that's a function which we want to call. It's kind of doing the same. It just sleeps. It is Tokyo here. It just sleeps for a few seconds, and then it returns the response as a success or error. And we want to call this from Java now. Okay. Well, if we try to do it in like an easy way, it won't compile because we can't call await in synchronous method. We can't put async as well on the method because we can't have an external. We can't have external asynchronous method. So what do we do? Well, we need runtime to execute our code, right? We need to store this runtime somewhere. Well, one option you can do is just have one cell, store Tokyo runtimes there, and just access it when you need it. It's straightforward, acceptable for most of the project. It's kind of easy, so I will not focus on it. I'll focus on alternative. Say I want to have the runtime associated with my JNI bridge. So if somehow I want to have two bridges running, they could have like independent runtimes. Everything is encapsulated. There is no global state. So what I can do, I can define a long field in the Java class, and I want to initialize it in constructor. So unfortunately, in Java, I cannot do native constructors, but there's easy workaround. We define init method, which we call any constructor, so we can do that. And so in init method, we create a runtime, we pack it in Arc, and if maybe some of you went to the cinterop talk, the next step would be familiar to you. You just call this into_raw method on the Arc, and what it actually does, it asks Rust, hey, please forget about this Arc. Don't decrement reference counter, just sort of not drop it, but like forget about it, and return me a pointer to this forgotten chunk of memory. Now you can cut this pointer to a JLong because they have the same size, and you can then get to access it later. Important to point, if you never call arc from raw on this pointer, you have a memory leak, okay? So let's see how we can get access to this runtime back. Now, as a helper method, there is a Java JNI API to get the field. We can now ensure that the field is actually long, and then we can call arc from raw, which essentially tells Rust, hey, I promise you this pointer was indeed created by arc into raw earlier, so Rust will then construct arc back, and note, neither from raw, neither into raw will modify reference counters. So that means once this arc is dropped, the memory would be released by Rust, right? And you should never access the field again once you drop this arc. So that will help us to do something, right, already. We can clean up after ourselves, nice. So in Java, we have this auto-closable interface, which all Java developers familiar with, and what's even better, all IDEs are familiar with. They will actually scream on Java guys to say, hey, you need to call close on this thing, it's there for a reason. They will suggest to use this thing called try with resources blocks in new, well, not new after Java 8 versions of Java. That's not new anymore, but even I think after Java 7. Yeah, so, and the close method, we can implement in very simple, we just get a field and drop it, right? And it's gonna release memory. I guess no one in Java will access it again after they call close. If you are really worried, you can set it to 0, for example, and check if it's not 0 later on. But okay, but what if we actually want to get this object, do something with it, and then keep it to take access to it later? Well, we can just call std memforget every time we call get field, but that's kind of messy because there's too many places and we'll forget it in one place. So we can do this nice little trick, and we just clone the arc which we got. We forgot original arc. Because we cloned, we implemented reference counter by 1, and we have 1 extra arc. So now we return it to the caller, and the caller can just drop it whenever it doesn't need it anymore, and it shouldn't even worry, it wouldn't even know that this is actually stored somewhere in Java. There's some native properties, and this was obtained from a pointer. Cool. So, okay, yeah. There are a few pitfalls there, actually. So first, what you do when you store in the pointer in Java long field. And Java developers, they don't expect pointer to be in the wrong field usually. And it's important to ensure that like user data, like if user puts some input, this input should not somehow like interfere with this long value, because then you will start accessing some restricted memory regions and this whole security mess. If you are really worried, if your application is sensitive, maybe actually consider using like one cell with some context and make it global, but like you don't have like pointers in Java then. Also, well, that kind of implies that Java should never read or write into this field, and the Java will then think that this field is unused because there is no references nor calls to it in Java. And so optimizer, for example, could get rid of it. So ensure, and IDE will scream on you, give you a warning, so ensure to annotate it. Likewise, you can see that we can access here by the name of the field, by the string, right? So if you have some obfuscation, then you should ensure that field is not renamed, right? Otherwise, you again will have problems. And I'm using arc in the example above. If you know, well, so everything in Java is reference counted, right? So you can kind of clone it uncontrollably, well, not clone, but clone references. You can move it across threads, not like in Rust, right? If you just allow you to call it from different threads. So if you're sure that it's going to be called from a dedicated thread, then you can actually just use box instead of arc, and then you can get mutable value and mutate it. If you're not sure, then maybe arc over mutex is kind of better. Then you'll have to log in every time your API is called. But then you can say like, hey, you can call it from Java, from any thread. I don't care. I'm gonna mutex it in the when you actually call my Java native method. So with this in mind, we can actually do our simplest way to call a async function. It's kind of horrible, but you remember we initialized runtime in constructor. We can now borrow it for a short period of time. And then we can just call runtime block on and then execute the function. The runtime, the async function would execute, give us some value back, and we will return it back to Java. It works. Yeah, some applications use it this way, no problem. Well, there is, however, a problem. The problem is that you're blocking the Java thread, which calls your method for some time. And how long is kind of not clear, depends on what async method is doing. Now, it's often going to be, well, some kind of critical thread. For example, it could be Android application main thread. And if you block it, then you get INRs, your app is unresponsive, the Google starts screaming on you like, hey, fix it, please. So what you're under pressure, what you do, I'll just spawn a separate thread to do it, and then it works. It now becomes responsive, but now you see, oh, well, why do I have 2,000 threads? Because you spawn a thread for every API, right? Okay, let's queue them into one thread and do it one by one, but then you have a throughput problem because requests which used to be parallel now become sequential, right? So in reality, if you use asynchronous runtime, there should be a reason behind it, and most likely the reason is this some asynchronous I/O, right, which you interfering with, and the whole idea of like asynchronous input/output is that you don't block a thread to wait for your asynchronous operation, right? That's the whole idea of why async was, in my opinion, like invented, and so any solution which involves blocking a thread, which involves calling block on, is like a bad solution because then probably your code shouldn't be async in the first place, right? So what to do, right? Well, what you actually want, you want to return a Java some abstraction and say, hey, this is like a delayed computation. I will complete it in the background and let you know, sort of that kind of abstraction. And there is abstraction in Java for that, well known. It's part of standard library of Java. It's called future. And what we actually want, we want our API to schedule a work on asynchronous executor and return a future back to Java, so Java can await whatever way, we will briefly talk about it in the last slide, in whatever way it wants on this future. So okay, well, how do we create a future? We need to return the future, right? So let's first create it. Well, creation of the future, we have this JNI API call, actually two, load the class and create a new instance here, and Rust nicely packs it into one API. One accepts the class. Well, the first parameter is the class name. The second is constructor signature, which in this case like void, and then arguments of the constructor. It will create a future. Now we need two references to the future. Why two? Because one we return immediately to Java, and Java can await on it later. And second one we preserve. See, we make a global reference out of it. Well, you don't see two here, but like it will be in the next slide. We will create a global reference. We keep it. And when our computation is finished by async time, we will complete this future from the native code, and we'll let Java know that, hey, we are done. So I mentioned two API calls. One is load class, and second is create a new-ish instance of it. And speaking of loading the classes in Java, yeah, it's a bit of a nightmare, actually. So there are class loaders there, and they're kind of tricky. So the problem, the class loaders are not like, it's like a global class loader. There's no class loader associated with a thread. They're associated with a class, actually, and they form a hierarchy. So each class has a reference class loader, which loaded this class. And then when class tries to access some previously unloaded class, it just uses class loader to load it. Now, the main class is always loaded by so-called like system class loader. But then Java can instantiate like a custom class loaders and load custom classes from somewhere. And basically they build up a new tree at this point of time, right? And it actually happens way more often you think. If you deploy on some application server which runs multiple applications on the same JVM, you most likely have separate class loaders. I've seen it happens even in Android. So if like if your JNI breach and your application is actually loaded by this custom whatever class loader, then the default one will not see your classes. Okay, so okay, when we call that new object, which internally calls find class from native code, which class loader is actually being used? Now that depends on when do you call that find class method. So by default, well, not by default, Java, what Java will do, it will look on your call stack, it will find the Java class on top of your call stack, maybe usually the one which made the native call, and will use the class loader associated with it. And usually it's no problem. But what if you spawn a thread which never been in Java, which just spawned, right? And you attach it, let's say, right, like as we've seen. Well, then the default class loader going to be used. And I've seen people like spending hours to trying to figure out, like, is there like typo in somewhere in this like class name? Maybe I should use dots instead of those slashes, maybe backslashes. But actually the problem is that you don't, well, your default class loader just doesn't know about your class. So there are two solutions basically to avoid this. Well, in our case, we use Future. Future is part of standard library. It always be there, so we don't worry. But if you load custom classes, maybe you pass, when you complete a Future, maybe you pass like a custom, object, instance of your class. Then you either have a method to load your classes before you spawn a thread in the context when you know that you're in a good context, or you can preserve this class loader and like call it back whenever you need to load, right? So just be aware of that. Now, completion of the future, when the computation is done, is actually not different from our previous example when we were calling Java back. We have an instance of future object. Well, we need it. We have the JNI interface pointer, and we just call method, pass all the arguments, the signature, the name of the complete method of the future, and the object, the J object, which represents the payload of result of your computation. Easy. So now, of course, before doing that, before calling this complete method in success case, I will talk about error case shortly. We need to attach the current thread, so we can do that using the API call, which we have already seen. Now you already know everything, basically. Like there's nothing much to show you, to be honest. And now this is how our final method would look like. So you see, we get our runtime pointer. We create our JNI future struct, which we declared. We get the local references, which we will return, you see in the end, OK block, right? And we wrap this future into like callback context. Now we can spawn a new Tokyo task. We can move in our callback context. We can call our async function. It will return either success or an error, just usual Rust result. And then we can call the callback method to send it back to Java. Nice. So there was a shortcut though, because we attached the thread here. Which thread did we attach? We actually attached the asynchronous runtime like Tokyo managed thread. And I mean, it's okay, it's gonna work. But if you do it, if you do this callbacks often, then you will keep like attaching, detaching the threads, and you will kind of block, it's not free operation, right? So you will kind of slowing down, blocking for a little bit of time the async runtime threads, which are not good. So the option to consider perhaps is instead of completion them in place, you can take your Java, like your struct representing the future, and the result of your computation, you can send it, or using, for example, the sync channel to a separate dedicated thread, which is attached, and then you just complete the futures one by one, because completion of the future is essentially supposed to be very fast. So going to be not much bottleneck. In worst case, you can have like a thread pool or something to do it. So that would allow you to, like, not to block asynchronous runtime and not to often attach detached threads. Well, what if things go wrong? Right? They usually do, right? So what to do? So there is this handle error exceptionally, which I'll show. Well, part of it. But before that, the things could go wrong in two ways here. First, they could go wrong like before we schedule everything. So we can't schedule because like you see question marks. So something is wrong, right? So in this case, we want this native call just to throw exception out, right? Let's see how to do it. And the second well, we'll see in a second how to do it. But the second kind of case where it could go wrong is inside the spawn block. So we schedule the job, but the job failed, right? It's some error, right? So let's see how to throw exceptions first. So exceptions in Java, they are actually like a flag in a native code, like some sort of global flag. So you can throw them using this throw new method, but it doesn't terminate the native code. There is no such magic to do it. Your native code will still go to the end of the function, whatever. You should usually like do some question mark or kind of like break. Now the return value of the method doesn't matter in this case. Java will not look into it because your method throw an exception. So you can just, like if your method is not void, you can just return like null. Actually, you see unwrapper default here would actually return null in this case, in case of error. So now, because exception is like a global flag, you can only have one at the given moment of time in the given thread. So you need to, the best practice is to check the exception before. Now, if you have exception, like you see, I have like just a, oh, I don't have any code there, but there are like options to do. You can clear it, you can get it and sort of stack it onto your exception. You can log it and you can just ignore and don't throw your exception. This is like up to you depending on what you want to do. It's sort of when you like, it's sort of like when your catch block actually, or finally block throws exception and you didn't clear previous ones, so it's kind of a mess what to do there in Java with those exceptions. Now, there could be a problem on throwing exception itself, like that throw new is getting the access of the class, and it's a custom class. Maybe you know you have this class loader mess, and it doesn't load your class. Oh, oops. And well, then you have like nuclear last result option, like crash the JVM with some human readable message while calling for an error. Yeah, so that's how to throw exceptions. Now, what if things go wrong in the asynchronous code? Like this response is coming from async method. So, well, we want to do a few things here. We want to create exception, don't throw it, because there's nowhere to throw. We're in background async runtime thread. So you want to create exception, and then we want to, the future provides a method called complete exceptionally, and then when Java awaits on this future, it will tell whoever awaits on it, like, hey, actually, you know, it's kind of panicked. There's an exception instead of your result. So create exception, you know all of this already. Not different from creation of any Java class, instance of Java class. Same new object call, class name, constructor signature, arguments, in this case a string. Now, calling complete exceptionally, nothing new here. Exactly same as calling complete. There is a call method API on JNI pointer. This object is a future. Name of the method, signatures, arguments. Now, I'd like to finish with how it looks in Java. So we call this native call, and it returns as a future. So what we can do, well, we can just block on it here and await for the result. That's kind of ruins the whole point. It's still better than blocking in native code because you can now interrupt it by calling interrupt. But if you call interrupt in your code, then something is bad probably with your Java code. What you can do, you can actually stack a computation on top of it. So you can call this then apply method, and you can schedule this closure to be computed when your Java code, well, when your Rust code is finished, right? When your Java code completes the future, then this then apply block would be called. Now it's interesting to reason where, on which thread this closure would be called. So I think it, by default, will be called on the thread which completed the future, which is your native thread, which often is not what you want. But the whole power is in that the completable future provides you an interface. You can pass the executor. So you can actually say that, hey, Java, whenever this future, which is coming from a native code, is finished, please schedule a job to process this on a different executor and pass this lambda. It's called lambda, it's not called closure in Java. So by doing this, you can actually breach your async runtime, Tokyo, for example, and any runtime which you use in Java, like often, for example, it's Kotlin coroutines. So this way you can breach two asynchronous codes, and do it safely. So thank you so much for that. So this QR code would lead you to my GitHub repository where you have all the code examples. You can compile and play with them. You can also I also uploaded the slides over there, and if you want to ask me questions, you can do it now, or here are my contact details to do it later. Thank you.
Thank you, Konstantin. We'll have a few minutes for questions and answers.
So you mentioned error handling.
Yeah.
I also write FFI code in Rust. But one thing is that you should never ever let your panics unwind into FFI code generally. But I even noticed in like the JNI documentation, they were like panicking everywhere. Is it like fine to panic into Java code? What happens?
If you panic in Rust code, which is part of the Java code stack. Now, if you look into this one, which one? Yeah, let me find it. The fatal error. Implementation will actually call panic under the hood. So normally what happens, your JVM crashes. Crashes on native code. You have a crash report. And on top of the crash, well, you need to look into the crash report, which produced by Java. And usually on top of the crash report, usually, you will have the stack, well, the name of, basically the message, a string. But I think it also depends whether you use like panic abort when you compile or not. I don't remember. I think if you use panic abort, then you might like, you will probably have like less debug information. But usually what you do, you compile it with the debug symbols, you strip the debug symbols, you keep them separately. When you have a stack trace based on the panic, then you symbolicate your stack trace, which you get like either, hopefully, locally. Maybe you can get it from the Google admin console if it's Android application. And then you just navigate to the source code where the crash happened, and it's going to be like roughly, well, it's going to be in the stack trace at least, the panic call. So this is not the easiest way to debug it. Why not? Like Java guys, when you give them the code, it's like, JVM crashes. Like, what? Well, you're crazy. Just rewrite it in Java. It never crashes, right? So that's going to be the response of your Java team. So if you can avoid panicking, avoid it. Throw exceptions. Exceptions, you can put like an error message, and people will see it in the debugger, and it's like, hey, your code throws exception. Here is a message, what I'm doing wrong. So don't panic. Try not to panic.
Any more questions?
I see the whole bridge is basically stringly typed all over the place. Plus, you provide arguments and constructors in a very dynamic fashion. So if signatures change or exception classes change or anything change, shit hits the fan. Any ways to avoid it? Do we have any code generation techniques that are available?
We're kind of avoiding half of those actually, because we use protobuf in my examples not to create classes. You will have so this is JNI bridge, right? Like this is actually, look, this is utility, right? Handle error exceptionally, and then you have this callback context function. So you can write them once, you can cover them with unit tests, and then your data is just schematized, right? So there is, unless you write some procedural macros which will generate those things, there's not really a way to avoid this. But even so, even if you write the procedural macros, it have to generate both Java and Rust parts, and you have to ensure to keep them in sync, right? So if Java will ever go out of sync, things will go wrong. Now, the solutions here, usually, which I try to follow is, well, I use anyhow here for handling just to make the presentation simple. But see, I put this context and error calling complete. So, for example, if you rename, well, this is future, but imagine it's not future, right? If imagine you call in your class, if you rename the method or change the signatures, this will fail with this context, there is an error message there, and then you can debug it because you throw it as exception on top in like some kind of unique way. So you can see at least like, hey, it was trying to get this method, it didn't find, probably something is wrong. Unfortunately, it's in runtime. So the only answer here is minimize your JNI bridge. If you can avoid writing bindings for data, avoid it. If you can generate your JNI API calls, it's not a bad idea because usually in a generated code, there might be bugs there, but you kind of find them, fix them. And then if you don't modify the generator, then you shouldn't have new bugs, hopefully. But if you then modify it, then you have it everywhere, though. But hopefully it's not very often. There is one question over there.
Thank you. One question regarding the exchange of data. If I got you right, then you serialize through gRPC and you copy data all over the place.
Mm-hmm.
Did you try to explore a stable memory representation like Arrow, for instance, does it, and then just copy handles over and basically let both environments like Rust and Java interpret those objects on the heap in the same way, and hence avoiding copy data all over?
Yeah. So the first thing I want to say, ideally, you want to minimize data transfers over your JNI bridge. Make those calls not too often and not too data hungry, so that the performance bottlenecks are reduced. So that is what you should try before you're trying to do some unusual techniques. But of course, maybe for some applications, it's not going to work. So there are a few things which we kind of briefly covered, right? So when we get data from Java into Rust, I guess here, right? This is where we can avoid copy. Obviously, because we use a protobuf, then the whole protobuf decoding is involved in a lot of copies. But if you don't use a protobuf, if you just if you just move the classes around, then you can do that. Now, when you send it back here's where the problem, right? If you send the stuff from a native code to Java, you have to allocate it on a heap, right? So you cannot do anything about that. Now, there might be situation when you need to get those bytes in Java, I don't know, maybe in Java you send it over socket, I don't know, or something. Then you have to give it to Java in the way Java can work with them, right? Sometimes you might wrap this vector into a struct, and then you can pass this just a pointer to the struct to JVMs, and you don't copy it, and then you have the whole APIs which are accepting the type-saved, in Java, type-saved references to all your objects, and so you just pay cost of the cross-language API calls, but you don't actually transfer data. So yeah, I didn't explore a frameworks which doing that idea, but which implementing this idea. But it's valuable idea for the applications which require often an intensive data exchange over the JNI bridge. So you sort of lazily, one option as well, for example, you create a class which has a lot of byte arrays inside, imagine, or a lot of strings. Now, you don't actually create a class, you create an empty object with a handler, and then you implement getters. And in the getter, you actually copy the data, right? So you create class instantly, you have pointers, it kind of auto-closable or something, and then you only copy the data when people need it. Now, the disadvantage of this approach is with Java people, they believe getter just usually gets value. It's not copying, right? So they might start calling getter a lot of times instead of caching it in Java. You can cache it in Rust, I guess, somehow. Well, no, you have to cache it in Java, actually. So, it's kind of getting, the whole code base gets significantly more complicated. So I would say do it when you have a strong need to do that.
Thank you.
Any other questions, anyone?
Any more questions? Okay.
Thanks again, Konstantin. We're going to break for lunch.
Thank you.
We'll be breaking for lunch now for an hour. Thank you.
Thank you.
Good afternoon, all. Good afternoon. Our next talk is hosted by Natalie, and she'll be speaking. Her title of her talk is Rustic Persistence, Automating PVC Life Cycles with Rust in Kubernetes. Give her a warm welcome. Thank you.
Hi, thank you so much. My name is Natalie, and today I'm going to be presenting about Rust as well as a little bit of infrastructure. The reason is I work as a staff cloud engineer, so my daily job not only focused on building and developing code with Rust or any languages, but also setting up infrastructure and managing Kubernetes is one of the job securities I have for so far. So my name is Natalie, I'm a cloud engineer, there's my LinkedIn. I'm also a AWS community builder, as well as I have a user group. If anyone in area like US or California and ever like to present, please reach out and come by and speak in our group. So agenda for today is I will touch a little bit on the Kubernetes ecosystem because I don't know how much everyone here knows about Kubernetes or works on Kubernetes. So to make this talk inclusive for everyone, I will touch a little bit on that. I will explain what Kubernetes operators are, what PVCs are, what these all words are about. But the main focus, it will be how we're going to use Rust to develop certain things for Kubernetes, right? And I will be not doing the live demo because it's a kind of a normal setup. So I will have a demo, but it's probably will be like going over the code and just covering those parts. And I will touch a little bit on developing things into production, how do we package them. I'm sure people heard about Docker, so things like that. Let's start. So Kubernetes. Kubernetes is an open source orchestration system, right, where a lot of different things happens and a lot of different type of application can be developed. Kubernetes, what it's good for is once you develop your application, it basically using different types of the system to develop, manage, control, and do a lot of things for us. But it does require some management, it does require some setup and configuration. The applications in Kubernetes are obviously containerized, so that's an important part. The operator I will be talking about is also before, like after we write the code or do anything without it, we have to kind of package it in a container. And yeah, the reason for Kubernetes existence is it helps as a developer to abstract infrastructure in certain levels from the application, right? So, to be honest, when you start with Kubernetes, most of us use Minikube or some other tooling, Key3, things like that. So it feels like it's pretty easy to just run Kubernetes applies and be done. But when you have a lot of clusters and do it in production, it's just impossible to do anything manually. That's why there is certain tools exist in the community. And in some cases, when you try to deploy certain things, they will have specific specs. You might heard about things like resources like deployments, pods, volumes, PVCs, or maybe you didn't. If you're interested, I would recommend going into kubernetes.io. It has all the details and amazing documentation, has been around for a while. But in some cases, all these standard things are not fitting the use case. And that's mostly happens when you have some proprietary resource that is hard to deploy or manage within Kubernetes system. And operators were designed as a custom resource of that ecosystem to add all things, gadgets we need in order to, let's say, help us to manage our application. I'm giving you an example. Some of us know what backups are. Usually with infrastructure, there is a tool called Valero. it's pretty popular, right? You deploy it. So Valor, in order to have a backup, it needs some volume to store this backup somewhere, right? So volume with Kubernetes, all the resources are usually not stateful. And let's say in some cases, someone could delete the resource because it's not needed, right? In order to, in specific cases, the deleted resource might have other dependent resources, right? So operator like that can help us to do a cleanup or take backup on a backup or do some other things. So everything around management, you can see on the slide, there is certain API, there is certain operator, and there are other system which kind of manages what's going on. And imagine this is completely automated, there is no manual interaction, it's just like living infrastructure. And now, if some of you here work a lot with Kubernetes, they might think, why do we need to use Rust? Because Kubernetes is written in Go, it's pretty popular language, and I would agree with you, but since Rust came in the picture and a lot of people in the community started developing with Rust, it's not super widely adopted, but I feel like it will change, I don't know, don't quote me on that. But I decided to just on this slide to represent a little bit of the idea that both languages are pretty good, but Rust has certain benefits in certain areas like performance, concurrency, or safety, which provide us specifically with the case of Kubernetes operators is a little bit of an advantage, right? So from the performance, yes, Go has concurrency. There is a lot of features that good enough to get you going, but things like, let's say, low-level memory management is not quite there, right? Optimizations in certain areas are not quite there. Similar Go routines we know we use, but there is a lot of kind of deep down critical asynchronous tasks that I learned that it's pretty much hard to do with Go, but it was really easy, not really easy, but pretty much reasonable with Rust. And obviously memory safe checks are not there, I would say, which Rust provides out of the box, and this is something I found useful, and yeah, that's my opinion on why we should start using Go with the Kubernetes ecosystem. So operators, as I mentioned, there are different resources. Specifics of the Kubernetes operators, it is a custom resource. So if there are different opinions, and some people would say that you don't need custom resource, but usually if they created by the ecosystem, there is a need, right? What I mean by that is after this talk, it doesn't mean that we all should go and start developing operators, but if we are in a situation where management of the application or some data volume is not handled by it, we should probably think about using it. So it's a process, right? What it does, it uses Kubernetes API to do certain things. For example, watch events, do certain actions, and react on those events. Everything with Kubernetes control loops, what it means is usually the resource have like life cycle, and someone usually watches for this life cycle. If you create a resource, it has a living time, and if it was deleted, there is something that will make sure everything was deleted, clean up, and we're ready to continue with the operations. So I want to say that this developing operators almost isolating us as a developers from like learning Kubernetes. Almost, I mean, if we do need to understand the API we are triggering, but that's basically it. So if I will be developing an operator as a person who needs to deploy the app, I would say it's just simplifying a lot for me. And this is where we kind of move to the different slide. So operators with Rust is stateful application for this use case, right? So PVCs are volumes. Volumes are stored data. Usually you don't want it to go away, specifically in production. So this specific operator is responsible for stateful application, and make them efficient. Also, operators will help us maintain the app. I call it the second day operation. It's a known term. So maintaining and managing will be provided with if you develop your operator correctly. And as I mentioned, usually it's a specific case. So there is a huge possibility of using some third party or specific need, the vendor agnostic thing, that's probably the need for Kubernetes operator right there. So let's begin with, so that was a little bit on the Kubernetes. On the operator, let's talk about how Rust can fit into this picture. So for this example here, I wanted to show usefulness of this presentation, right? And the PVC is something that I didn't find. So there is a operator hub that you can go, and there's certain things already provided, like Grafana operator, some other ones. But PVCs was in a long time a hard task, not just because of the backups. I can give you a different example. We all have secrets in the company, right? We store them in secret manager or vault. When we have things in Kubernetes, most likely it will go on the state application with the state. And it's really hard to manage your PVCs when you do things like upgrading the cluster or anything that requires even updating the vault, in this case, can affect the PVC or PV, where all your secrets are stored. So you don't want to lose them. That's why you want to design the operator in a way that no matter what happens, there will be certain prediction event of that, and your operator will react on certain action and will do things like delete or manage or create a new one, or let's say if you run out of memory, it can make a request or a claim, like we call it, for a bigger amount of memory and things like that. So for this task, my goal is to just create simple operator. There's PVC and PV involved. Again, PV is the storage that you have in a cluster, and request is something that your application is claiming for that memory. Usually one claim will have a PV. And for this example, my goal is to build a controller that will create something like cleanup action where someone deleted a PV, let's say resource was destroyed, I want my operator to go and clean the resource. And I also will have a monitoring around that, scaling, error sizing. So with Rust, apparently it's not that hard. There are two crates, which is kuberc and Kubernetes OpenAPI. Probably that will cover majority of the tasks. There is certain things that you might need to think, but these two will probably do all the work. And again, it will help. Everything with Kubernetes most of the time is asynchronous, so that's pretty good with Kubernetes. And it does have support for custom resources, because again, custom resources are not so common, although they're becoming more common these days. There's some reason for that. And you can build different watches, you can build different scales, schedulers, whatever you need. And with the Kubernetes OpenAPI, right, it's basically support for all the APIs that Kubernetes have, and then you can easily use that to talk to the cluster. I have done this kind of work many years ago using Python, and honestly, it was really, really hard to understand what API to call, how to manage that. So Kubernetes OpenAPI is something I really enjoyed from get-go. So I didn't have that weird learning curve when I had to go and understand the code, what this API is doing, and then write another different code to understand how to manage it. With Rust, this is just given. So Kubernetes has a page how you can build the operator. There's a known pattern. What do you need on your laptop or on your machine or on your server? Rest environment, cluster, Docker, kubectl. Kubectl is a CLI tool we use to manage, to talk to the environments in the, it could be different clusters. Usually you have kubeconfig configuration on your machine that has information of how do you authenticate with the cluster. And the other things I use are Tokyo, third log crates. That is pretty common. I'm sure everyone here familiar with them. So within my controller, within my main function, I would easily connect to the client. Sorry, I would easily create the client to use the API, initialize the client, obviously with the kube crate. There is basically, yeah, there is no need to cover it, how to do it any other way. And it also have error handling. So for line 23, I could just, it will fail not when you cannot access your cluster. It also will tell you, let's say, if kubeconfig is not there, so you can add pretty good error handling for someone who, for operator to report. And kube has kube logs that easily will be just visible once your operator will run. So controller components that I wanted to show in this example is reconciler, where all my logic for handling the PVC different states are, or could be. Error handler, basically some error handling to describe things that go wrong. And main RC, I also have a config, which I will cover later. It's not on this slide. And again, the state of PVC might change. It will go to the reconcile module, and config would just be described. So the controller part. Within the controller, I needed to handle things like, let's say you started the operator and then something went not as you expected, or the PVC will not bound once you run certain things. So obviously you need some feedback, and it's pretty easy to do it this way. Again, it's asynchronous. So in the end, I guess what I'm getting is that the custom controller, once you, and this is like for the simplicity of this talk, there are certain things you need. Obviously, there will be a logger, and I'm going to jump between these two slides because it's just how things are. So kube runtime, right? Imagine when you, so in your cluster, you deployed your operator to the, let's say, default namespace. You started it. So there is certain reconciliation process where you're trying to understand what's going on in the cluster, what PVs are there, how they attach, what things are happening. And then there's, so I created the object called PVC API that represents what controller will be managing. It will be only covering the specific resource. And if something goes wrong, basically the error will be shown. If you build in advanced operator, usually you want to add things like retries. You want to add things like, let's say when you delete PVC, if you delete the PV, the PV will be there for so long. There's in Kubernetes there's something called finalizer, which actually making sure that all the resources that are dependent still there until, let's say, certain workload has finished and things like that. So in your reconcile logic, you don't want to just put something simple. You want to have all the retries, you want to give timeouts, you want to have finalizer logic in the reconcile function, module. in order to make it behave like everything within Kubernetes. And errors should be very easy to understand, because in some cases, when user, let's say, did something manually, something went wrong, it's really hard because the login system in Kubernetes is really, it's busy, right? When you're trying to just run kublogs, it will give you a lot of different things. So you need to create the errors in a way that they just report on things that just happened or went wrong. In some cases, your application might not even going to fail, so there is no way for you to understand, okay, my PVC failed. Like, let's say if you ever use Longhorn, and I apologize if some of you might not. If PVC goes wrong in the Longhorn world, unless you go into UI, you see that something got detached, but there is nothing in the system will ever tell you that something went wrong. So like for systems like this, we want to use this controller and handle state of the PVC when it's detached. And then we want to add the error handling. Sorry, we not necessarily want to add the error handling, but in reconcile, we want to say, hey, if it's detached, try to reattach it because the PVC might still be there, PV might still be there, or if it's completely deleted, create a new one. And the same function you want to see, then your claim submitted the claim and PVC got the claim after it was created, the bond happened, then only then the whole setup will work. So what I'm trying to say that your reconcile should have all the like business and small logic, but it shouldn't just fail because it should try to restart and do much more. The context with that controller, obviously, just sharing the state among all the resources within your cluster. So this busy, it's visible. This busy slide will kind of represent the simple main function when you have a logger, you have your client, you have the API, then you have a certain config that I mentioned in the beginning. And again, config can be whatever you want to add and how big you want to build your operator. Then obviously the context and the controller. This is as much as you need to build the basic things for specific cases. To be honest, this is not enough when you start building productional things and cases, and let's say if your production environment has to be up with very, very little downtime with very, very good SLA. So the logic with I talked about reconcile. That's what by this slide I'm trying to describe. When you're thinking about your code, you want to cover as many cases as possible, and it should not be very simple in a way that there are options to recover your resource. If it's deleted, there are options to do a cleanup. So just deleting the resource doesn't mean that it's good, because if your resource, let's say, requesting the memory, and in some cases you have many, many, many resources piled up with the memory requests, by deleting them, that doesn't mean that all memory was freed up. So you need some, as I said, finalizer to go there and make sure everything was cleaned up and deleted. So in your reconcile function, put all this logic. So for my example, which I'm presenting here, reconciliation logic will look something like this. Again, with the Kubernetes, you can have different storage classes. If some of you maybe work with a AWS console, there is resources like GP2, GP3, there is IOPS, right? So all this called storage, and all of these are different classes. Just I'm trying to connect Kubernetes environments to something that you might have seen daily. And then obviously you do the, you build the PVC logic. In my example, let's say I want, as I said many times, that I want everything to be deleted. I want to add some good error handling that if something went wrong or if there is an event of the error, I want to try to recover the state of my resource. Error handling is pretty simple. You can make it the way you, config handling is pretty simple. In my case, it's just a storage class. The performance I want to add, I can add like threshold percentage. What it means is, excuse me, if my I requested the volume size. And then in Kubernetes, the different resources, different application might also have different requests. At some point, what might happen that all my teammates build the application that requires some memory, but there is not enough memory. My operator can handle this case by just checking if the threshold is reached. If not, or yes, it can add more if there is, again, if there is room. And that's higher level of infrastructure that's not going to be covered by this talk. Error handling, again, we're all familiar how to, we're trying to handle our errors in the best way possible. Obviously, we cannot cover all the cases in the world. So when you're just developing error policies, as I said, don't just break or fail. Try to see if the error is actionable, because the error you return to the user should be like really bad state where person might need to go and do some manual work. So best practices. Custom resources should be defined very simple in a way that the application already complicated. If you cannot find a basic resource which is up there and you're developing something custom, it has to be very easy to manage it. So think about your teammates or think about automation around it. API convention with Kubernetes are easy, and as I mentioned, there is a crate to do that. Handle the states properly. Basically, everything with the applications in the cluster should be properly stated. Error handling is there. The libraries we discussed. The performance. The performance of this operator is basically falls on the Kubernetes performance. You can, because it's a deployment, right? You can request as many replicas as you want. You can add the resource limits, and I will show it later on a different slide. And obviously, please document your operator. And if you know about security, try to follow the community guidelines. Although my opinion on security with Kubernetes is really not there as I would like it to be, but yeah, that's how it is. So if you wanna package this and deploy it to production, what do you need? Again, there's with the infrastructure and Kubernetes, the things we use daily is not like a personal laptop or coding or live code. We actually, as infrastructure people, we playing with the deliverables, how your apps are packaged. So in this case, you can put in Docker. There is no serverless or Lambda for operators, so it's purely just running deployment, which is kind of another application. And Docker build, Docker push, you create, so Docker container, you package it, you create your image, you push it in your ECR, whatever your company is using. This is the Docker Hub, Azure, whatever. And then if you use it locally, you can also create the registry with Minikube or with the Docker as well. And then if someone decides to play with it, install in Minikube, Minikube start, will get you there. I have two simple examples of the persistent volume and persistent volume claim, which is a PVC and the claim for it. As you can see, it's the minimum spec you will need. It's all defined in documentation. There is nothing complicated. I deploy it to default namespace, not a good practice, so keep in mind, but for local, be your own boss. So here is, as I mentioned, it's hard for me to do demo and presenting, so here's what I would run Minikube start, I would see the status once it's ready. For demo purposes, I would just apply both resources. In this both examples, when I check for my PV and PVC, you can see there's something already deployed and it's terminating, but the Rust stock PVC and PV are there, it was just created. So this is as easy as that. And then, just trying to see, okay, so it's visible. Deploying in a cluster. It's a deployment, so on the first, on the right top corner is a spec for it. Again, deployments are just defined in the documentation. The specific thing I have here is, oops, sorry, is over here. That's where I define resources for my operator. Here is what a kind of replication, how many of them I want to run in a cluster, things like that. and you can customize it in a way possible. And then once I run Kubernetes apply for this resource, or if you go into production, CI should do it for you, you will get my pods created, and then everything in the cluster needs access. So here is an example of the simple service account that someone who wants to try that in the real life will just need. And again, everything will be deployed in the service accounts are all over the cluster, so there is no need to define anything specific. So, key takeaways. The operator we did pretty much easily, can clean up unused PVCs, right? So it was easy to start, it was easy to build. I didn't need a lot of crates or a lot of overkill. The only thing I would recommend to going into asynchronous, like Tokyo, understanding how asynchronous task can build using reconcile function is important, and putting your logic there. Again, read on finalizers because there's some, like in my case, I use it for deleting the resources. And data persistence, which my PVC was trying to support, will be achieved in this case in a simple way. In some cases, as I mentioned, it's going to be a hard problem. So here's some links. I don't know if this presentation will be shared after that, but if you want to read on that, it's all here, and I appreciate everyone who came, and yeah, that's all I have. Thank you.
Thank you, Natalie. Really insightful. Does anyone have any questions for Natalie?
Thanks for the talk. When you write operators in Golang, there is a lot of scaffolding going on. Does cube.rs provide anything like that?
So there is no support for operators, but there is a support with the language itself. There is no scaffolding, but that's why I showed that slide with the pattern, which will have details how do you define custom resource. And that should kind of help to get started. But there is enough, so far, I'm sure there are probably some open source project, and I saw some of them. I just don't feel like they are grown enough that you can just use to scaffold anything like that. Also, it's pretty custom, and if you want to see the examples of the code, it's operators.hub or operatorshub.io. They have examples.
Okay, thanks.
You mentioned you did something similar with Python previously, and that here the API was a lot easier to grok. What about the result? Do you have any comments on whether the result of this was better or easier to work with than what you got when you did it in Python?
Harder, because asynchronous in general is really hard with Python. So when I was trying to solve the problem just to automate and abstract and make it a livable thing with Python operator, it was more like I have to monitor operator and have way more things around it. So let's say for this kind of scenario, I would not build Python operator, but there are certain things that still can be done even with Python. It's just not, you need a lot of concurrency and asynchronous support libraries to support that. So I would not recommend even looking into Python. But there, obviously, if you're just asking about there are libraries for Kubernetes, there are scaffolds on that. I just don't know if even hub for operators will have any Python in that. It's just, there's this language for the use case, and I wouldn't call, although I'm a Python developer, but not for operator.
Fair enough. Cheers.
Hi, thanks. I just wanted to make a comment on the code generation stuff, because you don't generally need to do scaffolding as you do in Go with KubeBuilder. It's more done by code generation, and that's the proc macro in KubeDerive that you can use. So, sorry, I'm Eirik, I maintain KubeRS. So if anyone wants to talk to me about Kube stuff, feel free to ask me later.
Nice to meet you. Thank you.
Sorry.
I feel special now.
Hi, thank you for the talk. I have a more like newbie question. So I just saw in the example code that you were like locking the config, and do I understand correctly that operator is like a single instance of resource in Kubernetes? Like, so why in the code you were like doing locking and like multi-threading environment?
Operator is like a pod.
So it's like a pod. It's like a separate pod.
It can go and up and be up.
Okay.
The things in this presentation, what it was managing is the PVC, which I don't want to delete. I don't want to go down. Yeah. But for the operator, it's a pod. That's why it has multiple replicas.
Okay.
You can
okay,
delete
that
it
makes
and
sense.
start it.
Thank you. Is there a way to test your operator without having to deploy it to Minikube and do all that? And
yes.
How do you write integration tests?
Integrationally or unit testing?
Both.
What kind of test? Integration, yes. Without Minikube.
Without Minikube.
Just the code part.
So do you have to run? So I'm developing an operator. I want to run it for the first time to see if it worked.
Right.
Do I have to deploy it to Minikube, run it, or is there an easier way?
I guess that would be my preference, but you can just deploy operator. It depends. Let's say this one is tricky and scary, and it was making sure that things are deleted correctly. I don't want to put it in production, but if I have staging, I would definitely avoid my development. If you're talking about like mocking and things like that, I probably would say you can mock the code part. With the KubeRS, you actually can try to, let's say if my PVC was deleted, no, that's probably not a great example. You can mock certain things with the APIs, that event happened, and then you can, but that's more like a unit testing. But basically you can try to build a mock. It's just a lot of work. I feel like it's easier to package Docker container, put it up there, but I'm just thinking different cases. You possibly could. I don't know a good framework, to be honest. I don't want to sound like I don't test my code. I usually do that, but I am in the space where most of the things I do, it goes from development staging, so by the time I go to production, I'm kind of confident in what I do. And I do things with the CI, if it makes sense. And like, again, Docker containers, all these things will be tested failing before. I have scripts where I test what my resources states are, but it's a good question, and I don't think I have done anything like that, actually. I should probably research. Thank you.
Thank you.
Were there any issues or limitations you faced when developing the operator with KubeRS that you think might have been easier with the Go operator SDK, for example, or was it all plain sailing in that regard?
So developing operators, actually, as I mentioned, is not easy because they come on a specific case. So usually Kubernetes have everything that we need. So in general, with KubeRS, connecting to APIs was easy. Obviously, providing all the configs are easy. So far, I found for my cases, which I haven't done, like it's not like I'm writing operators every day. That's why I'm presenting it, that it's rare. So far, it covered my cases, but what I usually do, I go on GitHub and check the issues. And then like, oh, this version, there is a one thing, I don't have my, there is, in some version, what I found, there was a breakage of the config and definition I had, but other than that, I feel like that's all.
Thank you.
And I couldn't pull out my code. I would tell you exactly which function is that.
Any more questions? No? I'll leave it.
Thank you so much again, everyone.
Good afternoon, all. As you can see, we have a super sub because Walter, unfortunately, couldn't make it. We have the amazing Tim McNamara giving us a talk entitled 4 Levels of Error Handling. Give him a warm welcome. Thank you.
Good afternoon, everybody. Hello to those of you who are on the live stream. Yes, this isn't exactly the same talk as you might have signed up for if you are joining for listening about Painter. You get a brand new experience of listening about error handling. I hope this goes well. Sometimes when you prepare a talk with 2 hours notice, it goes badly. We're going to get through it together. We could say that this is itself fallible. It's okay. My name is Tim McNamara. I run a little consultancy where we teach and consult on Rust, all the way from some of, in fact, the biggest, largest software companies down to indie game developers and so forth. And one of the things that is very important for people as they adopt Rust is understanding how to deal with errors. We start off with a very strange experience of not having exceptions. And yet, people say that Rust is a decent programming language. So I would like to spend some time talking about what your view of an error is and what the type system's view of an error is. Because these two things are actually distinct. Then I want to unpack result and sort of describe and sort of and here it's actually I've got a typo. Result as it's defined in the standard library or standard result has T and an E, but standard IO result has a T and standard format result has a T. And so one of the things that I want to show you is there is some sanity even though you have 14 or something different definitions of result in the standard library and other crates themselves have their own results. And then we're going to talk about starting with just ignoring the problem all the way through to ergonomically handling it. At least that's the agenda. But first I kind of want to chat, just a very small story. And you know, when I started Rust, I was like, well, I'm going to do something exciting. I'm going to write my own name to the screen. And, oh. It's like, I don't care about this Rust. Like, I just want to print it out. Like, should be, why? So Rust is very, very particular about requiring you to opt. It requires that you deal with the possibility of an error. So there is one difference between the result as defined in the standard library and other enums that you are likely to define yourself. And that is result has an annotation must use. It's essentially the only thing that makes it magical. And if you decide to ignore it, you'll receive a compiler warning. And so, just let to underscore. Okay, sorry, let underscore. And this actually works fine. This is what I mean by ignoring the problem, essentially. This gets the compiler or you just kind of wave it away. And then I thought, you know what, actually I should deal with this properly. I want to return format result unit. I can kind of sort of understand what's happening here. If you're new to Rust, the very last line returns the OK variant of result. Result has 2 sides, an OK side and an side. And the brackets or parentheses with inside OK is the empty tuple, or empty tuple, I can never say. And the term from mathematics is either the empty set or the unit type. And so essentially I'm saying this is a successful completion of the program. But later on, I really want to start expanding my program. And so I want to write potentially to a file. Here I am trying to open temporary hello.txt, and I want to write into that file, hello Tim. And I'm like, this is complicated, but I think I can get there. I initialize a mutable, I create a file, and then I open it up, and and then, sorry, the other thing I do is I write into it, and then I read it out, and I print the result from the file. And all of a sudden, I receive some sort of crazy compile error. The problem is that, so if you try to compile this program as is, you tie yourself up because the I/O module returns an error, its own error type, and so does the format module, and they collide. You kind of want to be able to return either or. This is not legal Rust syntax, but me as a beginner, I'm like, this is absolute nonsense. They're just results. This is kind of what I want to do. So the reason why I'm sort of telling you this is, and then I sort of learn about this kind of crazy syntax. And for me, I came from Python, so I didn't know what a box was. Rust taught me what a pointer was. And a box is an allocation on the heap, essentially is a link from the stack, the local variable space, into the heap, where it's kind of the space for sort of shared variables. Dynamic is an indicator of a trait object, which is I'm returning something which implements the error trait. And dynamic is a hint of dynamic dispatch, and is essentially a way of expressing the idea that I could return either a standard I/O result or a standard format result. And it will be resolved at compile time. The only problem with using a trait object, just generally, is that you lose the concrete type. You can only access methods that are defined on the trait itself. What is an error in Rust? You could think of an error as the side of result. You could also think of as an error as something that implements the error trait. These two things are actually distinct. Sadly, it's really complicated. The error trait has a very specific purpose, which is to be displayed in a log file or on standard out or standard error. That's essentially the only thing an error in Rust needs to be. Any type at all can be an error if it implements display. And so that's why sometimes we can return strings as errors. Because the role of an error for the type system is, or at least the role of things that implement standard error is to be displayed to an end user. Because something has gone critically wrong, or at least something has gone wrong in such a way that we might need to report it in a log file, say. Whereas result, if you go and check the standard library on your phone now, we can actually do it. Let's go have a look. Standard, Rustlang, and I go and look at result. And I see here that there's a T and an E side. And in fact, one side is success and the other is failure. But note on the definition that there is no trait bound on error on the E side. The side of result does not actually require that you implement the error trait. So it is mind-bending. And in fact, there are some really clever tricks that you can play. For example, in this, actually, no, I'm getting off task. We can talk, if there's time at the end, we'll talk about some of the clever tricks of essentially allowing this error side to this side to not implement error. Okay. So this is the full thing. It actually works. Yay! I've changed the program slightly. I've been able to get 42, and right down the bottom here, I'm parsing, and I am. I'll see if I can get my highlighter to go. There we go, laser pointer. The parse method is trying to parse in an I32 from the text file. And in fact, so now we've got 3 different implementations of error that our program could generate. But we sort of have this kind of interesting union of types through the trait system, through the trait object. But the programmer's view of an error is different. It's something that is exceptional. It's against the norm. We don't think that this is a normal behavior. It might also mean that there has just been something that is completely unexpected, and it's an error. Like it's, we don't know what it is. Whereas the type system is something that implements the error trait, and sometimes this is indirect because the type constraints themselves only require that you implement display. Result itself is just an enum that happens to be implemented multiple times, at least within the standard library. And let's go have a look what I mean by that. I'm not going to open up Steam, sorry. All of these results, oh gosh, no, apparently I am opening up Steam, look different. The pattern that the standard library adopts is that, so here's the central standard result is an enum. It's a concrete type with 2 sides, T and E. If I am the I/O module, the result is a type alias, and I specialize the E side to something that I control. And so essentially, I reduce the degrees of freedom. And so the pattern that the standard library follows is that individual specialized modules, they know the kinds of errors that they can generate, and they provide their own error type. But remember, and so they have often structs, sometimes enums, but typically structs, which are also called error. So we now have multiple things called errors. We have structs, concrete types defined within a specific module that is loosely associated with the error trait. But there's no implication that the structs actually implement error. In this case, it does. The I/O error does actually implement error, which is annoying to kind of have to say. But what I'm trying to point out here is that it's okay to be confused. Like, it actually is very complicated. Because result is just an enum defined in the standard library. The language, the compiler, doesn't know what a result is. Essentially, it boils it away and treats it like the same as, oh, my computer's deciding to freak out. Result is just an enum, and the exhaustive pattern matching of Rust is what actually provides the strength. Okay, so now I want to get onto these multiple levels. One is ignoring results. Let's go and have a look at what this looks like. I have some function which can return, I've got work here. Oh God, when my computer overheats, I think it's the graphics card, just kind of starts to go, I've got some work, and this can kind of, like, which say will return sort of standard error, standard result. and we have OK. In our case, we'll say OK, and then unit, unit. You might have seen this before. Some people just use unit as the error side as well. And OK, so we always succeed. And on the main side, we are going to return the same type. And that looks a bit ugly. So what we'll do is we'll define our type. Oh, actually, we won't. We'll do our type like this. And I will get to the point very soon, I promise. So work is a function which we care about, and let's say, appreciate it. And it's actually quite nice programming with other people. They're very kind. Sorry? So the compiler is a little bit confused because this also needs to return OK. And here I get the same error as we started with. That is, or at least a warning saying this is unused. And so I'll start first by ignoring the problem. Let underscore work will indicate to the compiler that you are making an active intentional choice to ignore the potential problem. This is on you as the programmer. If there is an error and you decide not to handle it, that's on you. So that is essentially what this underscore does. You are accepting responsibility for getting the information. Now, I said that we could have, let's say, invalid struct, invalid, and I can define, derive, debug, and then I need to implement display. Sorry, this is going to take me 2 minutes, probably less. Display for invalid. Come on. Am I giving a typo? Use standard path, that's not what I want. I know what I need. Standard format display. Impala. The implement missing members, and now I can write to this formatter thing, and I'm just going to rely on the debug implementation for my display implementation. And now I can return invalid. The compiler is happy, but I'm going to introduce some syntax or some code that you would have seen before, unwrap. What is the significance of unwrap? This isn't a trick question. Unwrap, happy to answer anything from the floor, maybe. I should watch the live stream live. Unwrap says, I know that this will succeed. And so go into the result and pluck out the OK side. So I'm essentially unwrapping the container. So you could conceptually think of this result as being some sort of container. And we're going in there and we're getting it out. We're opening it up and pulling out the unit. And what happens when, everyone would know that in this case we're going to panic. The thing will crash. And so one of the ways out of this is to start with an expectation of the error, which is, let's say, unable to work today, on strike. And now we get so we're on strike. We received an invalid. And we were unable to complete our work. So the only distinction between unwrap and expect is that expect provides a little bit of extra context to the output. But it does the same thing. But we are providing, we're kind of incrementally improving the treatment of errors. It's very common while you are getting started to use unwrap and expect. You're typically writing programs for yourself. You're writing command line utilities or maybe even small web APIs. And if the thing crashes, you fix the bug. It's okay. But one thing we can't, but you might have seen that pattern before where I provide this trait object. Because there are several sort of tutorials that say, oh, sometimes you just return a trait object. And this is error, error. And now I'll just demonstrate this. If I don't implement display, hopefully the compile will fail. Otherwise, oh no, it still compiles. That's very strange. Ah. So the question mark, sorry, apologies for getting a bit confused. Our work here is currently unused. If I try and open it up, we get this kind of issue that the type that I'm producing, this invalid, doesn't actually satisfy what the tutorial says that I should do and just provide a trait object. And the question is like, why is that? If you find yourself in this sort of situation, remember that you've satisfied the trait bound, standard error for invalid. There's actually no methods to implement. Now, hopefully, it compiles again. So you notice that the compiler error is wrong. So we need to opt in to the error trait, and now the type system can treat this invalid thing as an actual an actual trait object. And so the intuition that I'm trying to provide here is that the result type itself is not magical. The trait system is learnable. And if you start to define your own types for errors, you can start also to provide very, very specific diagnostics that are very useful to you. These errors are intended for your usage. Then, but there was something a bit odd, and that is I have an invalid, but I'm actually converting to a trait object. And so this sounds a lot like something that Rust doesn't enjoy doing. If you give it an integer, and say I've got A here, and it's 1, 2, 3, and this is an I32, and B is unfortunately for the type system a U32. Rust is going to complain very, very loudly that A and B don't play together very nicely. Rust doesn't like performing conversions. And so one thing to know about the question mark operator is that it's more powerful than just propagating up the error side to the parent scope. So it essentially is a short circuit for unwrap, whereby instead of panicking directly, it will push the error that I received from here's a better way to explain this. Match on work. If I match on work and there is an OK, then I return OK. On the error side, let's say I have some error, and this is an invalid. I somehow want to send back a, let's say I want to do this. This is what expect is doing. So this is expect. When there's an error, I crash. The question mark operator returns the error after conversion. So it also provides the ability for anything that implements error to operate as a trait object. So there are not many instances of what I would call hidden control flow in Rust, but this is one of them. The question mark operator also performs a conversion step to sort of unify the error types. And part of this is if you are defining your own error, you can implement the conversion utilities, the conversion traits. Say, for example, you could implement from for the kind of higher types. There's a little bit more. I'm teaching a lot about the result, which is useful, but actually I may have started with level 3. I might need to go back to level 2. There is one other point that I just thought would be quite useful. No, we'll get there. I'm sure that we will. So part of this thing of, let's say level 2 is, or level 1, we remember we were running expect with our custom error, essentially, or we were ignoring it. And what if I comment all of this out, and instead I return a string. And string from on strike. This is a perfectly acceptable thing to do while you are building your while you're sort of exploring the code. Strings can be used in the error side. They implement display, so they can be used as errors, and are arguably you lose some type safety because maybe tomorrow I wish to change this from on strike to something else, and a genuine enum would be a better thing to do, or we could say that the factory, no power to the machines. This is why we couldn't work today. We had a fault, or some. It would be nice if we could encode these problems in the type system, but right now, when you're starting, you don't need to. Or at least I would argue that there's other parts of Rust to learn. And the way to, so let's go up. So there's 3 is enums as errors. So instead of just having we can use a struct, but it might be interesting to say, the reason why we didn't, no work today. There was a strike, or I don't mean to be mean to people on strike, but it came up and we've got it stuck. It was like we had a power outage. And the other thing was a mechanical fault. Again, we can actually reuse this pattern of just deferring to the debug implementation for the display implementation. It's a good way to get you through the process. It's a better thing to do, sort of match on self here. And it's no work today. And actually take specific action depending on the enum, but right now we're doing example code. So over time, we increase the maturity of our little application. We started with nothing, we've moved to strings, we've moved to enums, we are providing proper diagnostics, and this is really useful to kind of develop the maturity of your code. As you learn more about the way that error handling works and some of this control flow with the question mark operator and a whole bunch of other bits and pieces, like how many results are actually in your code. The other thing to do I like understanding the way that things are operating before going to helper libraries. Because when you gain an understanding about how Rust works, it feels less magical. I don't like magic. It makes me feel very uneasy as a programmer. But a good thing, so here we have a cargo add, and I want anyhow. Anyhow is a really wonderful crate. If we, oh, that's the wrong place to go and visit. Excuse me. No, I'm getting very, very confused. I'm getting a bit lost. Crates.io, crates, anyhow. Anyhow returns, provides you with something that looks almost identical in its behavior as that trait object approach. Because, ding, 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 it uses the trait object's dynamic dispatch to implement what it is that you want. Except that it also provides you with the ability to add extra context messages directly at the call side. Lastly, there is another crate as well called this error, which expands on the enum approach, where I might, in this case, it's sort of we're interacting with some data, we're implementing a data store, there might be some disconnection that in the original error was from the I/O or standard I/O module, or unfortunately there's some invalid data, and then we have this kind of procedural macro for producing implementations of display and debug that makes sense. These crates, anyhow, and this error are both extremely useful. There are sort of another very a very strong competitor as well, called Air, which is slightly more comprehensive than just providing a context. We can kind of create, we can do more than, but there's a whole bunch of stuff here for you to explore, and oh, there we go, there's this error, and anyhow an error. So these two operate in the same way, they're kind of spiritual competitors. And they both use trait objects, whereas this error makes it easy to create an enum that could potentially compose errors that come from other places as well. Here are 3 really wonderful blog posts that take a very detailed look at error handling in Rust. They do take several minutes, do dedicate, and it's going to sound silly for a blog post, but there are thousands of lines of code, thousands of lines of very detailed, very specific, and very well written material. And that is 4 levels of error handling in Rust.
Thank you, Tim. I'm sure that will be very useful for many developers. We've got a little while to ask Tim loads of questions, so I'm sure you guys have questions, don't you? Yes.
We'll just wait till the mic, just to help the live stream.
Oh yeah, sorry. So I'm still fairly new to Rust. Thank you for the talks, very helpful. One thing that confuses me that I was wondering if you could cover is the like if let sum stuff. Like when are you supposed to use that?
So just the syntax itself, like what on earth is happening here? There's just too many words. Yeah, it doesn't seem to. It's almost close to English, but it's not quite. Right. So there's the question was, please tell me about if let sum. And you'll see this pattern when people wish to ignore the error side. And in our case, it's let's actually produce some actual work. Let's say it's like output. Oh gosh. Is work. And this looks very confusing. And there are alternatives as well, such as while. Oh, why is this unhappy? Okay, sure, of course. The compiler is angry at me because I'm promising it in my main function to return a result, but I'm essentially doing nothing. Now here is a, I don't want to do that. Why is this unhappy? Of course. So this is the sum. So what is sum? Option. One way to think of, so actually I'll answer the question and then we'll talk about sum. And just in terms of its relationship to results. Now, this looks very odd. The reason why this looks odd is because of a potential misunderstanding about like what let is actually doing. Let in Rust is more powerful than simple assignment. Let introduces a pattern. That it's introducing pattern matching and is saying that if this pattern matches, then assign any variables in the spaces that are there. So for example, I could potentially define an enum. Let's say here is another error, which is another thing we could actually be, it's like it's a weekend, right? Is it? And I don't know why I'm getting so fussy on the reasons why people aren't working today. So today's, and this could just be A. And I could assign A to a no work today because it's a weekend. And this kind of makes sense. That we're assigning a variable to an instance of an enum with the weekend variable. But I can also do something subtly different, which is if let no work today, weekend, equals A. Yeah. Let is a pattern matching construct. If the pattern matches, then proceed with the conditional. And by the way, the reason why we have this, sorry, I shouldn't say this because it doesn't make any sense to people who are watching the live stream who can't actually see me point. So what I've just highlighted here is a way to sort of test for equality without implementing the partial EQ and the EQ traits. And so it's very common to be confused by if let because it sort of feels backwards, it feels kind of odd. But if you think about it in the case of let introduces a pattern, and if that is satisfied, then proceed. For me, at least, that enables me to kind of untangle myself. Does that answer the question? Maybe?
So on line 27, if you remove the let, what would change there? Because it feels like it would be the same thing.
Ask that again, sorry?
On line 27, if you removed let, it feels like it wouldn't actually change the flow of...
Right. So why is the language... So this is... It feels like this is something that the language maybe should do. The problem is that the result of the assignment operator is a unit, not a Boolean. Actually, I don't know the reason. I'm kind of sort of half making this up, looking at the error type. But essentially, it's awkward. Yeah. 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 In the back. Oh, sorry. Yeah.
I don't have like a question in particular, but it's more of like a comment on the usage of anyhow and this error. From my personal experience in the big projects, these are, I guess, the main crates you can use for the error handling because they reduce the boilerplate for error conversions to none. So you don't ever have to care about what kind of the error types, different services or libraries you use return. You basically, the question mark makes everything for you. It has a very smooth and seamless translation between any kind of error type into the anyhow error. It also allows you to create your custom enum errors that will be compatible with anyhow error. So yeah, this is like just a very powerful tool that are very important in like any kind of big project where you have to at the same time use a one generic error for everything, but also keep a way to distinguish between different error types for different use cases. Like, I don't know, one error type for talking to the storage and another error type for like networking issues, stuff like that.
Yeah, and another way to say that potentially is that this is a huge amount of bureaucracy that I need to go through. And using anyhow removes a lot of that friction. I think we've got a hand up here. So thank you very much for the contribution.
Bit lighter weight, but since you're a Kiwi, I wanted to ask you your opinion on, I've been trying to popularize the name the Australian operator for the question mark, because every time I read an expression with a question mark at the end, I sound a bit Australian. So what do you think about that?
Fine. So the problem about being a New Zealander is you get confused with Australians regularly when you're overseas. But no, I like the idea of personifying the construct. One thing that I quite like about Rust is we have this word for things that are slightly odd, like turbofish. And creating things that and it might be the Australian operator. Now I immediately want to create like some other new name. But one of the problems with Rust is that it has lots of angle braces and it has lots of sort of brackets and things, and it's like ticks all, these backs. There's a lot of syntax and symbols, and giving them names is helpful, I think. And also it sort of softens it a little bit. So yeah, I think whether or not this solidifies to something like the Australian operator, it's kind of fun, kind of interesting, it's kind of a curvy country, sure. I mean, and I'm like, ugh, but yeah, Australia gets, all of the attention. But, we have better birds. No, actually, no, I like Australian birds too. They have a lot of snakes and a lot of spidey, bitey things, though. Further questions? hopefully this has been a, don't feel obligated to stay, by the way, just right to the very bitter end. Hopefully it's been an, oh, here we are. You know, I can also repeat the question. Oh, no, we're good.
Yeah, sorry to interrupt as you were wrapping up, but I feel like a few times, I'm struggling to think of an example, but I kind of end up in these nested, like unwrapping lots of nested result types. And my control flow ends up looking a bit weird, where I'm like, if this thing is okay, move on to unwrapping the thing inside. And yeah, do you have any comments on how to do that?
This came up yesterday, I think, just with Lars Bergstrom's talk around C++ and Rust. That Rust code often has this kind of rightward drift. And there are lots of relatively, sometimes there are many sort of if statements in around, so we kind of move, and it's quite indentation heavy. And it would be nice to, so there are a couple of ways around this. You can use patterns. You don't need to match on a specific okay. You could match, you say that you can actually match on, say, 2 results at the same time in one block. Now, so just to explain what I sort of mean, is that instead of, let's say I've got work 1, work 2, it's this is slightly awkward. It's not, if both days of the week were successful, then we proceed. You kind of create truth tables with your type system. That is and this is one way. The other thing that I quite like to do is, sorry, just before I say that, the problem with this approach is that there's no short-circuiting behavior. And so you are essentially requiring that your users do execute work twice. And if there was so it's not always appropriate. Another strategy is to, return, like essentially match on the error side rather than the okay side. And that way the okay flow is further to the left. Should we wrap up? Yes, we should. Thank you so much, everybody. It's been actually really, really fun. Feel free to reach out over the next couple of hours. I'll be here for drinks and so forth as well.